Hey everybody, today we are going to be working on identifying functions with numerical patterns. This video is going to consist of 3 parts. The first are some introductory examples, the second are numerical patterns, and the third will be identifying functions with numerical patterns applications. So to begin, we have an example here that says, given that f of x varies linearly with x, and f of -4 is 11, and f of 0 is 5, find f of 4 and f of 12. So we have a couple things going on here. We are given 2 ordered pairs, which are -4, 11, and 0, 9. We also know that it varies linearly, which means we are going to use f of x equals mx plus b. So we first want to find the equation that would fit these 2 ordered pairs, and then we are going to plug in 4 and 12 that equation. So we are going to plug in 11 for the y, because 11 is the y up here, and we are going to do m -4 plus 9. Now, here we just plugged in a x and y because we have that information, and 9 is the y-intercept, which is given by this set of ordered pairs, which is why we have a plus 9. Whenever you solve this out, you're going to get m equals -1/2, which is the slope. And since we have the slope and the y-intercept, now we do have our equation, which is going to be f of x equals -1/2 x plus 9. Now we are going to use this and we are going to plug in 4 and 12. So f of 4 equals -1/2 times 4 plus 9. This would be -2 plus 9, which is going to give us f of 4 equals 7. And then we are also going to plug in 12. F of 12 equals -1/2 times 12 plus 9, which is going to give us -6 plus 9. So f of 12 equals 3. Our next example states that given f of x varies directly with x and f of 2 is 15, we want to find f of 4 and f of 15. So varies directly means that we are going to use f of x equals kx. That's always the equation you're going to use when it varies linearly. And we do have one ordered pair here. It's 2, 15. So we're going to plug this in to this equation over here. 15 equals k times the 2. And we can, of course, solve for k, which is going to give us 15 over 2. Now we know our equation is f of x equals 7.5x. And we are going to use this when we plug in 4 and 16. So f of 4 equals 7.5 times 4, and this is going to give us 30. Then next we have f of 16 equals 7.5 times 16, which is going to yield 120. We next have, given that f of x is inversely proportional to x and f of 7 is 300, we need to find 14 and 28. So because it's inversely proportional, we are going to use the f of x equals k over x. This is always the equation you're going to use when something is inversely proportional. And we do have an ordered pair, 7, 300. So we are going to plug this into this equation over here, and we will have 300 equals k over 7. Once we multiply out, we will have k being 2100. Once we plug this back in, we will have f of x equals 2100 over x. Now we're going to use this equation to plug in 14 and 28. So we have f of 14 equals 2100 over 14, which is going to yield 150. That's our answer there. Now we are going to plug in 28 the same way we did with 14 for x. And we are going to get f of 28 as 75. And for our last introductory example, we have given that f of x is an exponential function with f of 3 equaling 12 and f of 7 equaling 36. We want to find f of 11 and f of 19. So right now we know two ordered pairs. We know 3, 12, and we know 7, 36. And we also know that the equation of an exponential function is f of x equals ab to the x. So we are going to plug in these ordered pairs for 12 equals ab to the third power and 36 equals ab to the seventh power. We're going to solve either one of these equations, it doesn't matter, for a. So I'm going to solve the first one for a, and that will give you a equals 12 over b cubed. We're going to use this to plug in our second equation. We're going to substitute the a, and we are going to get 36 equals 12 over b to the third power times b to the seventh power, which of course simplifies down to 36 equals 12 times b to the fourth. Divide both sides by 12, and that will give us b equals 3 to the 1/4 power, which is approximately equal to 1.316. So we have solved for our b, and we're going to plug that back in this equation up here, which will give us 12 over 1.316 to the third. A equals 5.264. Now that we have our a and b, we are going to put them into our equation for an exponential function, which is going to give us f of x equals 5.264 times 1.316 to the x power. And now we are going to plug in 11 and 19. So we have f of 11 equals 5.264 times 1.316 to the 11th power. And this is going to give us an answer of 107.927. And we're going to do this exact same thing for f of 19. We're going to plug that in for our x value, and that's going to give us an answer of 970.907. Now we are going to work on the patterns that you may see while identifying functions. Just as a quick note, the add pattern works for linear functions. So whenever you have a linear function, know there's an add pattern with the table. And there is a constant value being added to our x's and y's. So now we are going to find the equation from this. It's important to notice that we have been adding 2 to each of the x values to get the next x value, and we have been adding 7. You're always going to want to look for the pattern at the beginning because there are 4 different ones. You want to make sure you are applying the correct one. Now, this is simple because we know it is a linear function. So this is going to give us, first of all, the slope. M is going to be 7 over 2 because the change in y over the change in x. We, of course, have the change in y over here, over the change in x over here. And if you can recognize the pattern, you know that if we were to subtract 2 here, we would get 0. If we subtract 7 over here, we get 9. So that's going to give us our y-intercept. And that will give us the final equation, f of x equals 7 over 2x plus 9. Next, we have the add-multiply pattern. And a couple quick notes about this. It works for exponential functions. So if you ever see this table, you'll know that it's always going to be an exponential graph. And you are also going to add constant values to the x side of the table, and you are going to multiply constant values to the y side of the equation, or the f of x in our case. And we are going to look through our table, and this pattern does hold true because we are adding 2 to each of those, and we are multiplying each of these by 2.5. Now, we know that the equation for an exponential function is f of x equals a b to the x. And we know our a from these values. So that's going to give us f of x equals 6/5 b to the x power. And we can plug in coordinates. Let's just pick 2 and 3, which is going to give us 3 equals 6/5 b squared. And we can undo this by multiplying both sides by 5 over 6, because that will cancel that out on this side. And we are going to get 2.5 equals b squared, with b equaling about 1.58. And since we have our a and our b now, we can plug this into our equation, which is going to give us f of x equals 6/5 times 1.58 to the x power. And we have our finalized equation. We're going to be working with our multiply pattern. And a quick note on this, this is used for power functions. And here on our table, we can see that for the x side, we are always multiplying by 3.1. And on our y side, or f of x side, we are always multiplying by 2. So it's a constant factor of multiplication on both sides. Next, we are going to take our equation y equals ax to the b, which is, of course, the power function, and we are going to plug in two of these ordered pairs. And I'm going to pick the first two, but really any two would work. So here we have 10 equals a times 3 to the b, and we also have 20 equals a times 9.3 to the b. We're going to solve either one of these for a, it doesn't matter. I will solve the first one, which is going to give us 10 over 3b. Of course, I'm going to substitute that in for the bottom equation. If you do this, you will get 20 equals 10 over 3 to the b times 9.3 to the b. You can simplify that to 9.33 to the b. And to solve for b, we can divide both sides by 10, which would give us 2 equals 3.1 to the b. Undo that with logs, of course. You would have log base 3.1 2 equals b. And that is going to give us b approximately equaling 0.613. Once we have our b, we are going to plug that back in. So we would have 10 over 3 to the 0.613, because we're going to take this vector over here, and you are going to get a approximately equal to 5.099. So once we have our a and our b, we can simply plug that into our equation right here, and that is going to give us f of x equaling 5.099 x to the 0.613. And that's going to be our finalized equation. Our last pattern is going to be the constant second differences pattern. This will always be used for quadratics, if you have a quadratic table. And it is important to note that there are always the constant differences on the x and constant second differences on the y, which I am about to explain here. So as you can see on the x side of the table, we are adding 4 constantly. However, on the y side of the table, we are adding 60 up here, and then we're adding 28, and then we have a decrease of 4, and wow, a decrease of negative 36. So decrease of 36. And we are then going to subtract or add these one more time. So if you subtract, you're going to get negative 32, and another negative 32. So that's what I mean by constant differences on the x, but second constant differences on the y, you have to subtract twice or add twice. However you'd like to think about that. And then we are going to plug in any 3 ordered pairs from the table. I'm going to pick the first 3, and we will get 25 equals a plus b plus c. 85 equals 25a plus 5b plus c. And then 113 equals 81a plus 9b plus c. We, of course, want to get rid of the c's, so we are going to subtract these equations from each other, and we are going to get new set 60 equals 24a plus 4b, and 28 equals 56a plus 4b. Now this is nice because we have the same number for a coefficient of b, therefore those cancel when we subtract, and we are going to get negative 32 equals 32a. Divide both sides by 32, and we get a equaling negative 1. Next, we are going to plug that negative 1 in for one of these equations. Doesn't matter which one, but I'm going to use the top one. So we have 60 equals 24 times negative 1 plus for B. B is going to be equal to 21. And once we have our 21 there, we are going to go back and plug that in to one of our first equations. I'm going to choose the first one, really doesn't matter. 25 is -1 plus 21 plus C, and our C is 5. So once we have all three of our A, B, and C coefficients, we are going to go back and plug those into the general form of a quadratic, which is y equals ax squared plus bx plus c. And that's again what we plugged in for those. So we are going to get y equals or f of x equals negative x squared plus 21x plus 5. And that's going to be our equation for the constant second differences pattern. The last part of this video is an application regarding the identification functions with numerical patterns. So we have an object at room temperature, and it's going to cool down or warm up in such a way that the difference between the object's temperature and room temperature decreases exponentially with time. Our keyword there being exponentially with an exponential decrease. So suppose a cup of coffee is 70 degrees Celsius above room temperature when it is poured, but 5 minutes later it is only 50 degrees Celsius above room temperature. So we have two ordered pairs. They're going to have minutes in the x and the degrees Celsius above the room temperature as the y. And those ordered pairs are 0, 70 and 5, 50. That is a 5. All right, so we are going to plug these in for y equals ab to the x, which is our exponential equation. First of all, we know an intercept here with the 70, so we are going to plug that in for the a, and we're going to plug in our other points for y and x. So we will have 50 equals 70 b to the 5. And if you solve that out, you're going to get b is approximately equal to 0.935. And once we have our b, and of course plug this in to get our a, or if you remember, we already know our a, which is 70. We're going to plug that in for our equation, and we are going to get y equals 70 times 0.935 to our x. And this is going to be very helpful for our next two parts of this question. So this next question wants to know how high above room temperature will it be 10 minutes after it is poured. So we're going to use our last equation, y equals 70 times 0.935 to the x, and we are going to plug in 10. We're going to plug in 10 for our x, so we would have y equals 70 times 0.935 to the 10th power, and that is going to give us 35.71 degrees Celsius. That's our answer to part B. All right, the second part of the question wants to know how high above room temperature it will be 15 minutes after it is poured, which is very similar to the first problem, except we are plugging in a 15 for the x, not a 10, and that is going to give us an answer of 25.51 degrees Celsius above room temperature. And here's our final problem. Cold water from the refrigerator is 20 degrees below room temperature when a glass is filled, but 3 minutes later, it has warmed to 60 degrees Celsius below room temperature. How far below room temperature will the water be 15 minutes after the glass is filled? You should be able to recognize that once again we have two ordered pairs in a way that minutes is the x and degrees Celsius below room temperature is our y. So we have 0, 20, and we also have 3, 16. Just like the last problem, we are going to use y equals ab to the x because this is exponential. And we do know our a, once again, is 20 because we have this point here, our y-intercept. Then we're going to plug in this other ordered pair for 16 equals 20b cubed. And once we work this out, we are going to have b equals 0.923 via a calculator. And once we have our b, we're going to plug this in. Y equals 20 times 0.928 to the x. And the final part of the problem wants to know how far below room temperature it will be 15 minutes after the glass is filled, which you can simply get by plugging in 15 for the x, and that is going to give you 6.52 degrees Celsius. Thank you for watching. If you have any questions, please leave them in the comments.